Good morning, students. In last lecture, we have studied about thermodynamical terms such as equation of state. In that particular equation of state, we use that particular equation PV is equals to nRT. In that case, P is nothing but pressure, V is the volume, N is the number of moles, R is the universal gas constant, and T is the absolute temperature. Also, the next thermodynamic term, that is nothing but your thermal equilibrium. We explained that term. Adiabatic and diathermic wall. What is that adiabatic and diathermic wall? We also learned in last lecture. Some thermodynamic processes. There are 6 thermodynamic processes we see in short. Also, we are going to understand that thermodynamical processes in briefly later on. In last lecture also we can study 0th law of thermodynamics. Now in this particular lecture we move further for your next law of thermodynamics, that is your first law of thermodynamics, and we will see some of the explanation of the terms which we are using in the first law of thermodynamics. So the first law of thermodynamics, it is basically a statement of conservation of energy. In the 11th standard, we have studied about that conservation of energy. Energy can neither be created nor be destroyed, but it can be transferred from one form to another form. This is the statement of conservation of energy, and this particular conservation or statement of conservation of energy applied to particular any system in which that energy is transferred from its surrounding, or it will be transferred to the surroundings. So on the basis of that statement, we can explain that first law of thermodynamics. Also, this law gives the mathematical relation between heat, work, and the internal energy. Okay, so we will see some brief history regarding that heat and work. विद्यार्थी मित्रांनो, या ठिकाणी 1798 हे जे साल होतं, या 1798 मध्ये Count Rumford, the name of a scientist, that is Count Rumford, he studied about that heat, mechanical work and internal energy, and he observed that how much amount of heat is produced, that much amount of mechanical work is done. जेवढं काही amount of heat produce होईल तेवढंच amount of mechanical work done होतं, असं या ठिकाणी Count Rumford याचं ऑब्झर्वेशन होतं. But later on, that the famous scientist, that is Dr. James Joule, you have heard that name, that is James Joule, and he was from Manchester. He discovered that some particular relation between that heat and mechanical work done. He was shown that when the certain amount of mechanical work is done, an equivalent amount of heat is always produced. आता या ठिकाणी काउंट रूमफोर्डच्या अगदी विरुद्ध असं स्टेटमेंट या डॉक्टर जेम्स जूलने केलेलं आहे. रूमफोर्डच्या मते अमाउंट ऑफ हीट जितकी प्रोड्यूस होईल तेवढंच अमाउंट ऑफ मेकॅनिकल वर्क डन होतं, पण डॉक्टर जेम्स जूल म्हणतात की जेवढं काही अमाउंट ऑफ मेकॅनिकल वर्क आपण करूयात तेवढाच इक्विव्हॅलंट अमाउंट ऑफ हीट ही त्या ठिकाणी नेहमी प्रोड्यूस होते. That means if we say that W is the amount of work done, then and we can say that W is the amount of work done and Q is the amount of quantity heat or that will be produced by that particular system, then we can show the relation as W is directly proportional to Q. W, that is the amount of work done, and Q is the amount of heat which is produced. So that particular mathematical relation gives us that W is directly proportional to Q. Amount of work done, that should be directly proportional to amount of heat which will be produced. Okay. If we remove that sign of proportionality, then we have to add some constant of proportionality there, and that equation can be written as W is equals to J into Q, where this J is nothing but your Joule's constant, or it is constant of proportionality. So heat is energy and it will be transferred due to temperature difference between the system and the surrounding. Dr. James Joule, he was clear that particular idea regarding heat and mechanical work done. So that famous equation will be given by W is equals to J into Q. So work is energy and it will be transferred about by means that do not involve any temperature difference between system and surrounding. So basically heat आणि वर्क ह्या दोन गोष्टींना जर आपण कंपेअर केलं तर त्या ठिकाणी आपल्याला हे समजतं की हीट इट इज द एनर्जी ट्रान्सफर आणि एनर्जी ही ट्रान्सफर होते का हीट ही एनर्जी ट्रान्सफर करतं बिकॉज ऑफ टेम्परेचर डिफरन्स. सो देयर इज अ टेम्परेचर डिफरन्स. जेव्हा त्या ठिकाणी टेम्परेचरचा डिफरन्स आपल्याला मिळतो देन वी कॅन से दॅट हीट विल बी ट्रान्सफर. बट व्हॉट अबाउट दॅट वर्क? वर्क इज ऑल्सो एनर्जी ट्रान्सफर बट it do not involve any temperature difference between that system and surrounding. Okay, so this is the brief history regarding that heat and mechanical work done. Now we move further for the statement of first law of thermodynamics. So what is statement? We'll write here and side by side we'll explain it also. So it states that if some quantity of heat is supplied to the system capable of doing external work, then the quantity of heat absorbed by the system is equal to the sum of the increase in the internal energy of the system and the external work done by the system. So what is the statement of first law of thermodynamics? If some amount of or some quantity of heat is supplied to the system which is capable of doing external work, then the quantity of heat absorbed by the system is equal to the sum of the increase in the internal energy of the system and the external work done by the system. या ठिकाणी ह्या स्टेटमेंटचा अर्थ असा होतो की जर आपण काही क्वांटिटी ऑफ हीट, जसं की आपण म्हणतो काहीतरी हीट आपण जर एखाद्या सिस्टीमला सप्लाय केलेली असेल की जी सिस्टीम कॅपेबल असेल एखादं एक्सटर्नल वर्क करण्यासाठी, तर क्वांटिटी ऑफ हीट जेवढी काही त्या सिस्टीमने ॲब्सॉर्ब केलेली आहे that should be always equal to sum of that particular internal energy which will be changes by that or of that particular system and the external work done by the system. If you say that delta Q is the amount of heat supplied to the system by the surrounding is equal to, they will say that the quantity of, or it will be the equal to sum of the increase in internal energy of the system and the external work done of the system. If we say that there will be a change in internal energy which will be shown by that particular letter delta U, and the external work which will be done by the system is nothing but your delta W. So mathematically, this first law of thermodynamics can be written as delta Q is equals to delta U plus delta W. Here delta Q is the amount of heat supplied to the system. Delta U, it is the change in internal energy, of the system, and delta W is the work done by the system on the surrounding. So basically this is nothing but your first law of thermodynamics. Suppose if we write that particular equation, we can call it as equation number 1, that is delta Q is equal to delta U plus delta W. So this equation can be written in differential form. So this differential form will be as dQ is equals to du plus dW. So this is the amount of work done should be equal to sum of this change in internal energy of the system and the amount of work done by the system. Now we will see some thermodynamic sign conversion and for that particular heat and work, and we have to make some table here. So for your understanding, we should draw some table. So we draw here a table. In that table, we see some thermodynamic sign conversion for heat and work. So we'll understand that particular processes and then we will study it one by one. So if we say that first process is heat added to the system. If we provide that particular heat to the system, that means we have a formula delta Q is equals to delta U plus delta W. So if that heat will be added to the system, then we can consider its sign convention as delta Q is greater than 0, that is the heat is positive. जर त्या ठिकाणी आपल्याला अमाउंट ऑफ हीट जी काही आपण त्या सिस्टमला प्रोव्हाइड करतोय ती जर का ग्रेटर दॅन 0 असेल तर आपल्याला येणारं जे साइन कन्व्हेन्शन आहे हीटसाठी ते पॉझिटिव्ह असेल. पण जेव्हा हीट ही त्या सिस्टममधून आपण रिमूव्ह करतो, हीट रिमूव्ड फ्रॉम द सिस्टम, then we have a value of delta Q that will be less than 0, and that's why we can say that heat is negative. Okay, so this is all about heat. So when delta Q is 0, heat is positive, and when delta Q is 0 or less than 0, it will be a negative. Then about work, if we say that work done by the system, when that volume increases, at that time delta W is greater than 0, and if delta W is greater than 0, then work should be positive. या ठिकाणी जेव्हा आपण त्या सिस्टमचं वर्क डन कॅल्क्युलेट करतो, वर्क डन केव्हा कॅल्क्युलेट करतो, जेव्हा व्हॉल्यूम त्या सिस्टमचं इन्क्रीज होत असेल त्यावेळेस आपल्याला वर्क डनची व्हॅल्यू ही ग्रेटर दॅन 0 मिळते आणि आपल्याला त्याची साइन कन्व्हेन्शन जे आहे ते पॉझिटिव्ह मिळतं. त्यानंतरच्या केसमध्ये वर्क डन ऑन द सिस्टीम, म्हणजे ज्या ठिकाणी त्या सिस्टीम वरती वर्क होत आहे आणि अशा वेळेस व्हॉल्यूम मात्र डिक्रीज होत आहे. सो ॲट दॅट पर्टिक्युलर टाइम वी कॅन से दॅट डेल्टा डब्ल्यू इज लेस दॅन 0. दॅट मीन्स द व्हॅल्यू ऑफ दिस वर्क विल बी नेगेटिव्ह. ओके, द लास्ट इज अबाउट टेम्परेचर. when the temperature of the system rises, जेव्हा त्या सिस्टीमचं टेम्परेचर हे राइज होईल, then we can say that the internal energy should be greater than 0, that is delta U is greater than 0, and if the value of this delta U is greater than 0, then we can say that this particular internal energy is positive. And when that particular temperature of the system falls, at that time internal energy of the system is less than 0, then that time it will be negative. So this is some thermodynamic sign convention for heat and work. Okay, so we have particular equation as delta Q that must be equal to delta U plus delta W, and from that particular equation we will say that the quantities delta Q, delta U and delta W, they all must be expressed in the same unit. Either we can express this particular quantity in terms of joule, or we can express that quantities in terms of calorie. So all that three quantities, that is delta Q, delta U and delta W, must be expressed in the same unit. Okay. So we will make a statement about this delta Q and delta W and delta U. So dQ and dW, that means the amount of work done and the amount of heat supplied to the system, both the quantities depends not only on the initial and final states of the thermodynamic system, but it will be depends on the path of that thermodynamic system. आपण त्या ठिकाणी जी थर्मोडायनामिक प्रोसेसेस अंडरस्टँड केलेले आहेत त्या प्रोसेसेस पैकी म्हणजे आपण असं म्हणतो की ती प्रोसेस जेव्हा स्टार्ट होते त्यावेळेस त्या प्रोसेसला इनिशियल आणि फायनल अशा दोन त्या ठिकाणी स्टेट्स आपण कन्सिडर करतो. त्या प्रोसेस समजा आपण कन्सिडर करतो आयसोथर्मल प्रोसेस. सो आयसोथर्मल प्रोसेस विल बी स्टार्टिंग इनिशियली and isothermal process goes finally. That means that two steps are there. Initially both the bodies having different temperatures in isothermic process, and finally they will transfer their temperatures towards each other, and it will becomes a thermal equilibrium condition finally. So each and every thermodynamic process has initial and final states, and between that initial and final state, that thermodynamic process have paths. Okay, so this particular amount of work done and the amount of heat, both the quantities are depending on initial and final states of thermodynamic processes, and also it will be depends on the path of that thermodynamic process. So for your MCQ type questions, this particular line is very important. Next, that du means it is the amount of internal energy, and that amount of internal energy is depending on just initial and final states of that thermodynamic process. It is not depending upon the path of thermodynamic process. Okay, so this is all about that first law of thermodynamics. Now we're moving on the next important term that are used in the first law of thermodynamic system. आता ह्या थर्मोडायनामिक सिस्टीम मध्ये आपण काही महत्त्वाच्या टर्म्स आहेत की ज्या टर्म्स आपल्याला अंडरस्टँड करायचे आहेत. बेसिकली फर्स्ट लॉ ऑफ थर्मोडायनामिक जो आहे हा फक्त काय करतोय, डेल्टा क्यू, डेल्टा यू अँड डेल्टा डब्ल्यू या तीन क्वांटिटीच्या अराउंड फिरतोय. सो दीज आर द बेसिक टर्म्स इन दॅट पर्टिक्युलर फर्स्ट लॉ ऑफ थर्मोडायनामिक्स. ह्या सगळ्या गोष्टी आपल्याला माहिती. अमाउंट ऑफ हीट विल बी प्रोव्हाइडेड टू द सिस्टीम, अमाउंट ऑफ इंटरनल एनर्जी चेंज टू बाय द सिस्टीम, अँड दिस इज अमाउंट ऑफ वर्क डन बाय द सिस्टीम. सो फक्त ह्या तीन गोष्टींच्या अराउंड हा फर्स्ट लॉ जो आहे तो त्या ठिकाणी नेहमी अडकलेला असतो. सो इफ ऑल ऑफ यू सबस्टिट्यूट द व्हॅल्यूज ऑफ दॅट थ्री टर्म्स, then or we can say that you can substitute the values with the proper signs, then we can get that particular problems that you are able to solve, and that nothing but your correct problems. So आपल्याला काय गरजेचे या तिन्ही गोष्टींचे साइन कन्व्हेन्शन्स जे की आपण या टेबल मध्ये बघितले, हे साइन कन्व्हेन्शन जर तुम्ही प्रॉपर यूज केले या फॉर्म्युल्यामध्ये तर असा कुठलाही न्यूमेरिकल या पर्टिक्युलर फर्स्ट लॉ ऑफ थर्मोडायनामिक्स वरती नाही जो तुम्ही सॉल्व्ह करू शकणार नाही. So let us understand each term one by one for an identical or that ideal gas system. So first term आपल्याला या थर्मोडायनामिक सिस्टीम मध्ये किंवा या फर्स्ट लॉ मध्ये जी आपण यूज करतो ती म्हणजे वर्क डन ऑन द थर्मोडायनामिक सिस्टीम. So work done or by work done by a thermodynamic system. थर्मोडायनामिक सिस्टीम मध्ये आपण हा पहिला वर्ड यूज करतोय, त्याला आपण थोडंसं एक्सप्लेन करूयात. आता आपल्याला हे तिन्ही वर्ड्स एक्सप्लेन करायचे, जसं वर्क आहे, इंटरनल एनर्जी आहे आणि अमाऊंट ऑफ हीट आहे. या तिन्ही वर्डला आपल्याला एक्सप्लेन करायचंय विथ द हेल्प ऑफ सम थिअरी. ओके, सो वी ऑलवेज से दॅट वर्क डन बाय द पर्टिक्युलर सिस्टीम और वर्क डन ऑन द सिस्टीम. आपण नेहमी काय काय म्हणतो की एक तर वर्क हे त्या सिस्टीमने केलेलं असतं किंवा त्या सिस्टीम वरती झालेलं असतं. म्हणजे या पर्टिक्युलर दोन शब्दांना आपण नेहमी त्या ठिकाणी वारंवार उच्चारत असतो. सपोज द गॅस इज कन्फाइंड इन द सिलेंडर. आपण काय करतोय, इफ वी कॅन टेक दॅट पर्टिक्युलर डायग्राम फॉर पिस्टन. ऑल ऑफ यू नो व्हॉट इज पिस्टन. सो आपण एक कन्सिडर करूयात की दिस विल बी अ सिलेंडर and in that cylinder the gas is confined. Okay, so this is the gas molecules. Okay, so gas is confined in the cylinder with a movable piston. Suppose we'll say that the piston is there, we'll consider this a particular cylinder and a piston is there. So this is called as a piston. Piston manayat. Okay, so these particular molecules which are present here, that will be acting on this particular layer in the upward direction. So all that molecules exerting force on that particular area which will be exerting on that piston. So this is the particular diagram which will be having a work done during expansion. So this is the diagram for expansion. So when that particular gas molecules, this is a gas, it will be confined in that particular cylinder. When that gas molecule will be exerting some pressure on this particular wall of the piston, then it will be moving through this infinitesimal distance dx. That means that piston will be pushed outward by that particular gas. So if we say that the force, some amount of force will be exerting on this wall, the piston, or we can say that the system move with some distance dx, and this particular piston will be moving in the outward direction. So we can say that the work is done on that particular system. Okay, so we can say that P is the pressure. Here we can write the variables. This is P is the pressure which will be on that particular pressure piston. Then A is the area, and this is the area of the piston, we can say that, and some F is the amount of force which will be exerted by the gas on the piston of that particular cylinder. So we have the basic relation as force is equal to pressure into area. Okay, so with the help of this particular equation we will be explain that particular work done which will be done by the system. So we can take here the equation of force. Okay, now आपण त्या ठिकाणी बघितलं की पिस्टन वरती जसं वर्क डन झालं, तर वर्क म्हणजे काय, आपल्याकडे एक जनरल फॉर्म्युला आहे वर्कचा, that is nothing but your force multiplied by displacement. So here force is F which will be exerted by that gas on the piston, and it will be moving some displacement dx there. So we can say that the amount of work done, or that small amount of work is there, that should be equals to force multiplied by displacement. So here F is the force and dx is the displacement that will be made by the piston. Okay, now all of you know that force is nothing but pressure into area. So we'll put the value of force, that is pressure into area multiplied by this dx. All of you know that area multiplied by displacement, that is nothing but your change in volume. So we should write this pressure as it is, and instead of this area into displacement there should be a change in volume. So it will be dV. So we get that equation for amount of work done as P into delta V. Here we should write that A into dx, that should be equals to change in volume. Since okay, so we get that particular formula as dW is equals to P into dV. Okay, now this is for a particular small work is there. If we say that there must be a change in volume, that is dV, so volume can be changes from its initial position to final position. So if we get that particular volume change, so for that volume change, and it will be changes from initial to final position. Okay, so initial means it is VI and final means VF. Then the equation should be written as, this is the work done, that is W, and it is the integration of dW, where that volume can be changes from VI to VF. Okay, so this is the finite volume that will be changes from VI to VF. Then this work done is given by integration. This is the definite integration VI from VF, and that is the integration of dW. So where the value of dW is P into delta V, if we put that value in that particular equation, we get that integration of P into dV. Okay, that will be limit goes from VI to VF. In that case, what is dV? dV is the change in volume. So we can say that volume will be changes from final position to initial position. So after putting that value of integration, we should get that particular equation as P into VF minus VI. This is the final volume minus initial volume is nothing but your change in volume. So the final work done is given by this particular formula, this formula, and this formula also. Okay, so this is the change in volume. In that particular case, जर आपण हा बघितला तर that should be nothing but your small. Okay, so in that case, what is this P? P is constant. Okay, if we say that P is the constant term, so from that equation of state, we have an equation of state. What is that equation of state? That is PV is equals to nRT. So we have that equation as PV is equals to nRT. Okay, so in that case, V is the volume, and volume is very small, that will be changes. So we can get that equation as P into dV, that should be N into R. And what is this T? T is nothing but your temperature, and temperature is also small. So we can write that temperature as delta T. Okay, so we should write that delta V, and this is delta T. So for a small temperature, there must be a small change in volume. So P into delta V is nothing but your work done, that should be equals to N into R, that should be multiplied by delta T. Okay, so we get that equation for W as NR into delta T. In that case, N is the number of moles, R is the universal gas constant, and delta T is the small change in temperature. That means it will be changing from its initial position to final position. So finally, we should write that formula for work done as work done, that should be equals to this NR are the constant values we can take outside the integration, and integration of delta T, where that limit goes from Ti to Tf, that is initial temperature to final temperature. So the final equation for work done is given by N into R into that change in temperature, that is from final to initial, that is Tf minus Ti, and this is also work done in terms of temperature. So when variation of pressure is there with volume, जर आपण त्या ठिकाणी pressure with volume जर आपण consider केलं variation, then that particular term is known as area, which will be bounded by that PV graph. So first of all, we will take that PV graph. What is PV graph? If we draw on x and y axis here we can take volume, here we can take pressure. Okay, suppose that volume will be decreases like this. So we can take these 2 points here like this. Okay, so this is a particular P1 and this point is V1. Okay, then this point is P2 and this point is V2. So here the coordinates are P1 V1 and here P2 V2. So there must be an area under this graph. So that much amount of area under this graph, and this particular area under the graph of PV. This particular graph is known as a PV graph. L PV graph manto. So we have an equation for work done, that will be P into dV, integration of P into dV, and that volume goes from initial to final position. So this is the equation we have, and that equation is applicable for this PV graph or the area under this particular graph. Yeah, a graph चा जो area आहे that will be bounded, that pressure and volume variation. So we can say that this work is done that must be equals to area under PV graph. Okay, so this is also the work done. Okay, so basically we conclude that from this particular equations, this work done is a path dependent quantity. Work done is a path dependent quantity if, second conclusion is there, if volume is constant in a particular thermodynamic process, then work done is 0. Next conclusion is, if volume increases, then work done is positive, and if that will be decreases, then work done will be negative. And for a cyclic process, work done is positive if cycle is clockwise, and work done is negative if cycle is anti-clockwise. So these are some of the conclusion from this work done. So this is one of the important term which we are using in the first law of thermodynamics, that is work done. So this is all about this work done in a thermodynamic system. Now there are some numericals which are based on this first law of thermodynamics and the work done. So we can take that particular numericals in next lecture. Till then, it will be goodbye.